Welcome. My name is Marloes Mul and I'm an associate professor at IHE Delft Institute for Water Education. In this video, I will provide a brief introduction to the global challenges for water and agriculture. In this presentation, I will explain the current and future challenges in providing sufficient food, feed and fiber for a growing population, and I will specifically dive into the relationship between different water resources and agricultural production and how are they being affected by climate change. Let's first start with where we are coming from and how we've been able to feed the growing population in the past century. A large part of the global agricultural lands and therefore production comes from rain-fed agriculture, and 80% of the rain-fed farmers are smallholder farmers, supporting rural livelihoods. As is indicated by its name, rain-fed agriculture is highly dependent on sufficient and reliable rainfall amounts. Its extent has been relatively stable over the last several decades due to limited suitable areas. There's of course natural variability of rainfall between different years as well as within the season. In many tropical climates there's a distinct rainy season followed by a prolonged dry season, during which agriculture is not possible without irrigation. Farmers therefore can grow one or sometimes two crops per year. Rainfall also varies one year to another, with some regions experiencing more variability affecting their agricultural production. Climate change, therefore, can have serious consequences for rain-fed agriculture, not only affecting the total amount of rainfall, but also shifting the start and end of the rainfall season to increasing high-intensity rainfall events and prolonged drought. While rain-fed agriculture produces a large part of the global food production, irrigated agriculture is largely responsible for the required increase in production due to its ability to produce year-round and multiple crops, and is often located in areas with favorable climates for agriculture. As an example, the global production of cereals increased more than 200% since 1964, with the majority of this increase stemming from intensification in irrigated land and only 10% increase in the harvested area. Although still about 80% of the agricultural areas are rain-fed, the expansion of irrigation is mostly responsible for the increase in production. Not only has the irrigated area doubled in the same time, irrigated lands on average produce 76% higher yield compared to rain-fed land. This doubling of irrigated areas also requires roughly the same increase in the use of water resources, responsible for more than 70% of all water withdrawals. Expanding the irrigated areas therefore not only has impact on land resources and land degradation, it poses a real challenge on the water resource availability, especially in water-scarce regions. To reach this intensification comes at a cost. About 10% of the agricultural land has been degraded and approximately 1.2 billion people are living in agricultural areas with severe water constraints. Looking into the future, needs for food, feed and fiber is expected to increase with the world population reaching close to 10 billion by the year 2050 and exceeding it by the end of the century. Although there appears to be sufficient good and suitable land which can be directed to agricultural purposes, realistically there's little room for expanding agricultural lands which do not have severe environmental or social costs. Focus should therefore be on dealing with the degraded lands and sustainable agricultural intensification of the existing agricultural lands. Additional challenge is the climate change, which is expected to increase global temperatures between 3 to 6 degrees by 2050, and changing rainfall patterns and increased incidence of extreme events such as floods and droughts. Changing climatic conditions may affect the suitability of crops in specific areas, where some areas become too hot to grow certain crops, or the rainfall patterns no longer suit the crop, for example by shortening of the rainy season. Areas with higher temperatures have higher crop water requirements, and in areas where this does not go hand in hand with an increase in rainfall, the water demands increase water stress in areas of water scarcity. In the next slide, we will further unpack the two sides of water scarcity, from the agricultural demand to the water availability side. Crop water requirement is defined as the amount of water required to compensate for the evapotranspiration loss. The evaporation loss by crop depends on various factors for crop type, crop stages or phenology, and climatic conditions. The climatic conditions are represented by the reference evapotranspiration component of the equation, ET0. This reference standard evaluates the crop water requirement of a reference crop, grass, using the Penman-Monteith equation. This is based on various climatic variables such as temperature, relative humidity, wind speed, and radiation. Expected increase in temperature will increase this reference ET component. The crop-related factors are captured in crop coefficient Kc in the equation. During the crop development stages, this Kc value changes from low value in the development stage to the maximum value in the mid-season stage, after which the Kc declines again. This means that the highest crop water requirement happens during the flowering and grain filling stages. For many crops, the crop water requirement during the peak development stages exceeds the reference crop water requirement, illustrated by Kc of more than 1. Overall, the crop water requirements of a specific season depends on the duration of the specific stages and crop water requirements, as calculated using the presented formula. Information about typical Kc and duration of the different stages for a large range of crops can be found in the FAO 56 report. The crop water requirements are not necessarily the total amount of water needed from the available water resources. In areas or periods where there is rainfall, the irrigation water requirement is defined as the difference between the crop water requirement and effective precipitation. Precipitation which is stored in the root zone of the soil and can be used by the plants. The total amount of irrigation water needed also depends on the area cultivated and the irrigation efficiency of the system. If there is sufficient water in the system, the water withdrawals of the irrigation system are determined by this calculation of irrigation water requirement. This distinction is also translated into green and blue water concepts, whereby the water that evaporates as a result of rainfall is considered green ET, and the water that evaporates as a result of irrigation, whether it's from surface or groundwater, is considered blue ET. The amount of green ET is commonly seen as a part of the natural water cycle, whereas blue ET is seen as a result of human-managed water resources, and the over-abstraction can lead to water scarcity. From the different concepts, it's clear that climate change can affect the amount of water needed from the water resources. First, increased temperature and changing climatic conditions increases the crop water requirements, often not supported by an increase in production. At the same time, changing rainfall patterns, reduction in seasonal precipitation, or even increasing high-intensity rainfall events reduces effective precipitation, requiring more water from the blue water resources. When insufficient water is supplied to the crop, it affects the yields proportionally, if all other conditions are the same. The yield response factors provide an indication on how a crop responds to water stress. Drought-tolerant crops generally have a smaller reduction in yield compared to the reduction in evapotranspiration. On the other hand, water-sensitive crops are more affected by water stress. In addition, water stress during specific stages of the crop, such as tasseling and grain filling, have more impact on the yield than water stress during the other stages. When we discuss water resources availability for agriculture, two concepts are important: water scarcity and droughts. Water scarcity occurs when there is not enough water to meet all demands. Certain regions in the world therefore are always considered water scarce. A way to evaluate water scarcity is to assess at national level the amount of renewable water resources there are per person per year, where below 1,500 cubic meters per year is considered water scarce. In such conditions, increasing agricultural production relies mainly on increased use of water resources, exacerbating the water scarcity problem. However, countries in the more temperate climates with increasing competition, competing water demands and climate change also face increasing challenges of water scarcity and creating environmental problems. Drought, on the other hand, is more related to deviations from the normal. A naturally occurring dry season is not considered a drought, which also means that low rainfall means different things in different climates, as in some areas they are part of the normal variability and in other cases they are considered droughts. As a system is generally adapted to certain conditions, and deviations from the normal poses serious challenges. In the field of droughts, there are three types of droughts according to the OECD. Meteorological drought, referring to a prolonged period of low precipitation. Agricultural drought refers to a condition where soil moisture is insufficient to meet the needs of crops and vegetation. And finally, hydrological drought occurs when surface or groundwater levels drop below average over a prolonged period. Of course, these droughts are all linked. As water resources dwindle, it has an impact on the agricultural sector. With climate change, the occurrence and frequency of droughts are expected to increase globally. Based on this short introduction to global challenges for water in agriculture, we can conclude that the required increase in agricultural production is mainly expected to come from irrigated agriculture, requiring substantial amount of water resources. Already the largest consumer of water, its continuing demand for water will increase water scarcity and stress in more regions globally. Increasing temperature due to climate change will not only increase the agricultural water demands, but also affect the water resources availability. It will also likely increase the occurrence of extreme events such as droughts affecting the agriculture production. It is clear that water and agriculture are closely related, and careful monitoring and management of both water resources and agriculture are needed to successfully address this global challenge. Thank you for your attention.